Let's get started on Chapter 6, Math 65B, so otherwise known as Calc 2. This is what's called integral calculus, generally speaking. Before we get started in the new material in Chapter 6, I want to do a brief review of Riemann sums and the definition of definite integral. Because just about every other integration formula we derive at this point uses the concept of a Riemann sum. So let's take a look. So first, let's let f be defined on a closed interval from a to b. So let f be defined on the closed interval from a to b. And let P be a partition of AB. So be a partition of AB. So a partition would look like this. We say, so that is, and I could use like IE right there, but so we say A is equal to x naught, which is less than x1, which is less than x2, etc., to x sub n minus 1, to x sub n, which will be b. So what you end up with are these intervals. You end up with intervals x naught to x1. And then you could say the next interval is x1 to x2, etc., like that. Okay, then you get to your second to last one. You could talk about we'll talk about the kth interval that's in there. I'll just do it right here. How about that? So x sub k minus 1 to x sub k. And then you go all the way to the nth interval, which would be the x sub n minus 1, x sub n. That equals b. All right, so these keep in mind, these are not all equal lengths. Okay, and so our partition on an interval will look like this. Okay, so you have the interval from A to b, and you have x1, x2, x3, x4, etc., like that. And then you have x sub n minus 1, and you would keep going, right? Or let me just say it like this. Let's just make that the kth interval somewhere in here. So x sub k is in here somewhere, and then you would keep going. So notice that when you're looking at this, you don't have equal lengths of these partitions. That's actually on purpose, because you don't want to take one and then infinitely break that one up. You want to take the whole thing and define the largest one to be the norm. So we want the norm to be broken up, and then now this is the norm, and then break that up even more. We'll get to that in a second. All right, so then okay, I defined that down there. Okay, so the Riemann sum, let me change back to white here. Okay, so the Riemann sum of f for p is the sum. So you have the sum as you go from k equals 1 to n of f of, and then you could use different letters, but in this case I'll use w. W sub k delta x sub k. So that's the kth interval where w sub k is an element of this interval. So it's x sub k minus 1 to x sub k. And it's arbitrary in here. So it could be this endpoint, or any value in between. Because we make it arbitrary, if needed later, we can make it specific. So it doesn't matter what it is right now. Okay, and then k goes from 1 to n. And delta x sub k is equal to that difference, right? It's x sub k minus x sub k minus 1. Okay, so that is what we call is the length of the kth interval. So it's some arbitrary interval in here is what we call the kth interval. Not sure why that's highlighted like that. Okay, so whichever one that is, suppose it's this one. All right. So now let's talk about the norm. So the norm of the partition I realize too when I'm doing these videos, you can if you're writing stuff down, it might take you about the same amount of time as me. But if you write it ahead of time, you want to listen to it, you just fast forward it. You probably already know that, but I realized that the other day you can just fast forward it because I'm writing and talking, so it takes a little longer. Where if you just want to get to certain things, you could use like 1.5 or something to go through it. It works pretty good. Anyway, so the norm of the partition, P, is denoted with the double bar like that, is the length of the largest subinterval. So is the length of the largest subinterval. So like I was saying back here, this may be the norm, and we're going to want that norm to go to 0. So you would basically you end up getting more partitions, but that's kind of implied. So the definition of the definite integral looks like this, and I'll show you kind of some pictures of that too as we go. So the definition of definite integral. So you say the integral from a to b, and that's like a this is literally means like elongated s, so it means sum. So you want to picture all these things as sums. It's the sum from a to b. So that is equal to the limit as the norm of the partition approaches 0, and then it's the sum over all the k's of f of w sub k delta x sub k. So once you take this limit here, then you get the exact amount of whatever that is. So if f is positive, hopefully you've seen this before, and if not, it's in the book, if you can go back and review stuff if you need to. What you're getting then is some function like this, if this is f, and if you go from a to b, then you get what? Yes, you get the area under the curve if f is positive. So there's all those statements, of course, too. So when you add this up, let me change back to that. Just make it this color. Okay, so you get this area. So let me show you how this works with the norm and stuff. Okay, so that's your region, and you get area here. So that's your R. We call that often R, region R. So a to b, and then so let's say right here, this is x sub k minus 1 to x sub k. Now I went to that exact little spot here and here, but just pretend it could be anything, okay? It could be here, it could be here, whatever. I just went to here because it's kind of nice. So we're going to go like this, and your delta ends up being this length here, and then times the height. Well, the height is the function value, right? That's why you get the height. So you you break this thing up like this, and you get the And it could go a little higher. So this would be maybe, this is your W sub k. So maybe this right here is your W sub k. Remember, it could be anything inside that interval. And so now your height is going to go up to here. And it's not exact, right? I mean, this is a little overestimation. This is underestimation right there. And so, but each one of these, this is the height and that's the width of this rectangle. And then you add them up, right? You keep going across. So hopefully you'd seen all this before. So you keep going across. You might do a really big one, right? And you add all those up. Then once you take the limit going to 0, the norm of that partition going to 0, they shrink, they get small, right? You look at the largest one, you break it in half or whatever, make it smaller, and then you get another larger one, and you break that one in half, and you just keep going like that. Okay, so that's a Riemann sum. And so what we'll be doing now, okay, so now here's the basic idea, just to give you a heads up. We're going to take this little sliver like this, and we're going to revolve that around the x-axis and derive a formula based off of this Riemann sum. And we'll look at that next. So 6.1 is volumes of cross-sections, the disk method, and the washer method. So this is called so what's next is solids of revolution. So we'll do that in another video. We'll do a couple, probably in 6.1 with a few examples. And then we'll get on to 6.2, which is volumes of cylindrical shells. And yeah, that'll be probably the first week. Okay.